Hey guys, Math 6610, and what this video is on, and I'm just going to title this Intro to ANOVA. Not that videos need a title, but kind of seems appropriate. And what ANOVA is, it's called analysis of variance, and it's a way to, it's a statistical test to test the equality of group means when we have more than two groups. Give you a little history on the process on ANOVA. It was developed by Fisher, and Fisher, I'm going to say probably did this somewhere around the 1920s. Actually, probably a little bit before the 20s, somewhere after World War One. You know, when we talk about the prominent statisticians, I don't think anybody's list would not include Fisher. When I think of the prominent statisticians, I think of Pearson and Friedman and John Tukey. But Fisher's clearly going to be on everyone's list. But anyway, guys, to get the ball rolling on ANOVA, we can revisit a two-sample pooled t-test. Now, a two-sample pooled t-test would seek out to test the equality of two group means with equal variances. So the assumption when conducting a two-sample pooled t-test is that the variance for the first population is equal to the variance for the second population. So what we could test is we could test that group mean 1, or I'm sorry, population mean 1 was equal to population mean 2, which, if you think about it, this is the same thing as saying the difference in the means is equal to 0. Okay? Now, what ANOVA does is it builds on this, but it tests the equality of more than two groups. So we have, just as before, we have population number 1, which has a population mean and a population variance. These are unknown. Population 2 has a mean and a variance, which is also unknown. But we have more than two groups. And we'll say that we have K groups. So K is greater than 2. Now, what we end up doing here is we end up looking at a null hypothesis that is similar to what we did with a two-sample pool t-test, but we assume that the population mean for all the means for all populations are equal against the alternative, at least one pair of means is different. Now, you might ask, and again, let me be completely thorough here, with the assumption that we're drawing from populations that have equal variances. So that's one of the assumptions that we have when we conduct an ANOVA. All right, now a lot of people say, well, why do we need this fancy schmancy ANOVA test? Why not just conduct multiple t-test? Well, the answer is multiple t-tests inflate the what we call the family-wise type 1 error rate. Now, Let's just do a simple illustration here. Uh, let's say we have 4 groups. So we have group 1, group 2, group 3, and group 4. And we could clearly test the group means, examine group means between 1 and 2, between 2 and 3, 3 and 4, 2 and 4, 1 and 3, and so on and so forth. Well, you can show that if we have a 0.05 probability of committing a type 1 error on this one, we also have a 0.05 probability of committing a type 1 on this test. We have a 0.05 probability of committing a type 1 error on this test. We can show that by conducting all of these multiple t-tests, that we can approximate the probability of committing a type 1 error by 1 minus 0.95 raised to the 4th power, where this is 0.95 raised to the k power, which clearly is 4 groups. I think this turns out to be about 0.185. So what we can say is about 18.5% of the time, or at a probability of 0.185, if we conduct multiple t-tests, we are going to inflate the type 1 error rate that we set at 0.05 over triple. So we're going to be 3 times more likely to commit a type 1 error by conducting multiple t-tests than we would if we conduct an ANOVA. So that's at the end of the day what we seek to do with ANOVA. The main goal with ANOVA is to control the family-wise type 1 error rate to usually 0.05. We don't want any of this crap 0.18, 0.19, tripling the chance of committing a type 1. So that's what, again, what ANOVA does is it controls the family-wise type 1 error rate. Well, guys, how's this all work? Well, just like any test, we start out with certain assumptions. And the most important assumption for ANOVA is independence. This just tells us our samples are not related. Second assumption we have is normality. We assume our populations are normally distributed. And the third thing that we have as an assumption for ANOVA is we assume we have what's called homogeneity of variances. So we assume, just as we talked about before, that the variances of the populations, of the K populations, is the same. Now, let me give you an illustration of what happens here in ANOVA. It's kind of cool, actually. Or at least I think it's cool. Every time I say something like it, I think something's cool, I always think my daughters, of course, they think I'm the biggest geek that ever walked the planet. And when I say something like, math is cool, they always laugh at me and give me a hard time. But they'll learn one day that math is cool. All right, gang, here we go. We have these populations. And for this illustration, I'm just going to say we've got 3. So what we do is we come in to the population number 1. We pull out a random sample of size n sub 1. We calculate the sample mean, called x bar sub 1. And we calculate the variance, which we call S1 squared. Dive into population number 2, set a sample size, calculate the sample mean, calculate the sample variance. Same thing here. Set the sample size, calculate the sample mean, calculate the sample variance. From this sample data, we will calculate what's called the F-statistic. And the F-statistic is going to be calculated by examining the ratio of what I'll call the variance of between divided by the variance of within. All right? Now, what's this tell us? Well, first and foremost, based on our assumptions, we know that we have samples that are not related. We have independence. The second thing we know is that these populations that we're drawing from are normally distributed. Nice, smooth, neat distributions. None of this stuff. None of this stuff. None of this stuff. We have normal distributions. The second assumption is we have equal variances. So equal variances tells us that the normal distributions that we're drawing from have similar variances. They have similar shapes. So to give you an illustration, we don't run into something like that with our distributions, where clearly this population variance would be bigger than that one. So we work up here with the assumption that, again, we have normal distributions, and we work with the assumption that these kind of look like ghosts, don't they? And some, okay, maybe they don't. And we look like that they have, let's just think about the same shape, the same variance, okay? Well, here's what happens. We assume that the, okay, let me back up here a little bit. I'll bring that back in just a second. It's a well-known fact in test of hypothesis, when we create a test statistic. And guys, I don't care if we're doing a Z statistic, a T statistic, a chi-square statistic, an F statistic, whatever it may be. Higher test statistics lead to lower p-values. And lower p-values are more evidence against our null hypothesis. All right. Now let's think about this this F statistic that I told you about. It's the ratio of the variance between over the variance within. Well, because we have an assumption that these variances within the distributions are the same, we can kind of control this value. And how do we make a ratio bigger if we control the denominator? Well, by making the numerator bigger. Well, the variance between the distribution, what this does is it kind of comes in here and examines a grand population mean and examines the difference between kind of looks at an average here. It's kind of a weighted average. It looks at the average, or the distance, again, between the distributions as compared to this grand mean. So if this distribution would happen to be over here, then that would increase that value, which would add to the variance between, making this a bigger number, hence making a bigger F-statistic, hence making a lower p-value, hence making more evidence against the null hypothesis. And again, the null hypothesis is that all the group, that the population means are equal. Well, it turns out that even, in my opinion, gets even a little bit cooler. Now, what's the formula? Well, the formula for the F-statistic turns out that we give this variance between and variance within fancier names. And the variance between we're going to call the mean square factor term. Now, some textbooks call this the group term. That's fine. Divided by the mean square error. And sometimes you see this referred to as the mean square for the residual. Guys, these break in to two parts. The mean square factor is the sum of squares for the factor divided by the degrees of freedom for the factor. The mean square error is the sum of squares for the error divided by the degrees of freedom by the error for the error. So guys, ultimately here's what our F statistic, how it is calculated. Let's do the degrees of freedom first. The degrees of freedom for the factor term is just k minus 1, so the number of groups minus 1. And the degrees of freedom for the error term is n minus k, where n is the sum of the sample sizes that we took from each population. The sum of squares for the factor, we sum from I equal 1 to k. And what we do here is we take each group mean minus the grand mean quantity squared. And then the sum of squares for the error is the sum from I equal 1 to k of n sub I minus 1 times the variance of each group. So guys, what we end up doing here is for each of these populations that we're drawing from, and let's just do the illustration again. Just k equal 3. That'll certainly make the point, and we can generalize from there. So what we do is we come in, dive into that population, if you will, and we pull out a random sample of size n sub 1, which has sample mean x bar sub 1 and sample variance s sub 1 squared. We get a random sample from population number 2. We call that n sub 2, size n sub 2. The sample mean, as you would expect, would be x bar sub 2, and the sample variance is s2 squared, s sub 2 squared. And same thing. So this is an estimate of mu1, this is an estimate of mu2, this is an estimate of mu3, this is an estimate of the variance for population 1, estimate of the variance for population 2, and so on and so forth. Guys, it's important to note N1 doesn't have to be equal to N2, doesn't have to be equal to N3. Typically, many times when you design your study, that's the way it happens. But sometimes it doesn't, and that is perfectly fine if it's not equal. You don't want a huge difference in your sample sizes because you get into kind of power issues. It does affect the power a little bit if there's a big difference, but nothing too crazy. All right, gang. Some notation that we have. I think all of this is so additional notation. The CapEx bar is the grand mean. So that would be the grand mean of all the samples. And of course, we have to use the weighted mean there. We talked about cap n just being the sum of all right, let's see how this all works out. Now, one thing to keep in mind before we go any further, this F-statistic follows the F distribution, degrees of freedom k minus 1, comma n minus k. The F distribution is not bell-shaped and symmetric like the T distribution or the Z distribution. So what we'll do is we'll come in, we will calculate the F statistic. The area to the right of that is the p-value. We don't concern ourselves with any two-tailed test in the F distribution, at least we don't usually. And of course this distribution is going to be the F distribution, degrees of freedom k minus 1 and n minus k. So I'll illustrate that with some real live numbers going out here starting right now, and let you see how that all plays out. All right. Now, guys, I got a data or a well. Yeah, here we go. I have a something I want you to look at, kind of a motivating example, if you will. So since the data below represent quiz scores out of a possible 50 points for 3 professors, Dr. A, Dr. B, Dr. C, and looks like we've randomly selected, looks like 987, right? So about 24 students have been randomly selected, and we've recorded the professor they took and their. So let's just think about this as like kind of like a final exam score. And for some reason, someone suspects that there may be a difference in group means across Professor A, Professor B, and Professor C. All right, gang, first thing you'd want to do here is get this data into R. And I've already done that, so let me show you what I've already done. I've come in and set up the data set as it should be set up. So let me get out of the exit full screen thing here. So what I've done, you know, it's so tempting, and I'll really be able to tell the students who I've connected with and the ones that I haven't. It's going to be very tempting for some students to put these things in column form, because that's kind of the way we work on the graphing calculator. Well, guys, we're moving into big boy, big girl stuff now where we're not going to do that. So 32 and 31 and so on and so forth. And of course, B would be 2931 and C would be 2734. That's not the way we do things once we get at this level. What we want to do is we want to set up a data set that has on the rows our cases and in the columns our variables. So when I come down to a particular row, everything on this row needs to pertain to my sixth student. So I know that this student right here scored a 34 on this quiz, and they had Professor A. You know, I could come in here with maybe gender. I could come in here with classification. And let's say that this was this person was a female, and let's say that they were a sophomore, and this person was a male, and this person was a freshman. So I want to allow it where, again, set it up like a data set. Rows represent a particular person. And if I set this up the way I had it before, where we had Professor A, Professor B, and Professor C, that wouldn't be the way. This row right here would be the first scores for each of the professors. Well, guys, that doesn't make any sense. As much as I preach that, some of you are going to challenge me on it, and I'm going to win. You're going to be doing stuff over, and I'm going to act real pissy, and so guys, don't do that. Let's set these things up appropriately. Now, next thing I'd want to do is come in and save this. I'm going to do a save as. I've already done that. I prefer the names of data sets to be something short, 3 or 4 letters at most, because when we open it up in R, I want to keep it simple. I prefer that you save this to your desktop, and I want you to save this as a .csv, comma separated values. Now, guys, be careful, because there are other .csvs that you can choose that will not work. I've done a lot of work on trying to figure out the easiest way to get data into R. And the easiest way that I have found, and the most stable way of getting the data in, is to set it up in an Excel data an Excel spreadsheet, converting it to .csv, and it opens seamlessly in R. So, guys, choose this one, not the ones at the bottom. Save it. I'm going to replace and hit continue, and we'll close that down because I don't need it anymore. And I don't need that anymore either. And I don't need that anymore. All right, at least for a while. All right, guys, let's open up R. First thing I want to do is set my working directory, and I can get my working directory first, and I see it's set at users ddarbro. That kind of helps me determine the form I need. And I want to set my working directory as the desktop. My data, I just call it data. I'm going to use the read.csv. I kept it short because I don't want to think too hard about what I named my data set. I need to attach it, and I always like to just take a look at the names. So I have 3 variables here, ID, score, and professor. And I'm ready to make some things happen, okay? Now, there are certain things that I'm going to need, so I think it's important here to come in with a split screen. I think it's going to work nicely. And, some of this stuff, you're going to think, what's kind of redundant that I'm doing it, but keep in mind we got an extremely small data set here. The next data set you have may have 600 people. So you're going to need a more systematic approach to finding some of this stuff. So, gang, the first thing I'd want to do is find the sample sizes. So I would use the t-apply for my score over my profs, and that is found by going length. So, guys, one thing I know is that N1 is equal to 9, N2 is equal to 8, and N3 is equal to 7. Let's find our sample means. All I have to do is just hit the up arrow, change length to mean. So X bar 1 is 35.89. X bar, the sample mean for Professor B, is 28.75. and x bar 3 is 32.57. Now, I don't think there's anything wrong with examining the data now. You don't want to make any conclusions just yet, but I think it's fine to look at these mean differences. Again, these are sample mean differences. These are not population mean differences. We can't conclude that our ANOVA is significant. We got to let the process play its way out. But right here between x bar 1 and x bar 2, and this is actually for Professor A, for Professor B, and Professor C, there's a pretty significant usually means less than 0.05. I don't know that yet, but there's a difference there that captures my attention. I don't know if this 32 to 28 will be enough, but it looks like to me that this 28.75 difference to 35.89 could lead into something. Next thing I want to do, because my formula needs it, is I want to get my variances. And guys, variance is easy to do. So I have 10.61, 31.36, 11.62. And is there a red flag? Yeah, it seems to me there is. The lowest variance, or I should say the highest variance, is almost 3 times the lowest variance. So it looks like to me there's a red flag here that we have violated the assumption that our population variances are equal. It doesn't appear to me, based on what we've collected from our sample, that this is a reasonable assumption. Next thing I'm going to need my entire sample size. Well, all I have to do there is just do length of one of my variables. So I have 24 total scores. And I need my grand mean, so I can just go mean of my score. So 32.54. All right, let's calculate our F-statistic. We're all set to do that, right? So the F-statistic is going to be four parts. First of all, on the top, we're going to have our sample size times the sample mean minus the grand mean square. Sample size, sample mean minus the grand mean squared plus sample size, sample mean minus the grand mean squared, and my degrees of freedom will be k minus 1. We have 3 groups, so degrees of freedom 2. I'll go ahead and come down here. My sample size is 24 minus 3. So my degrees of freedom here are 21. So we know that this F statistic will follow the F distribution, degrees of freedom 2, 21. Okay, the sum of squares for the error will be the sample size minus 1 times the variance plus the sample size minus 1 times the variance for Professor B plus the sample size minus 1 times the variance for Professor C. All right, let's make some calculations here. I've already done a little bit of the work because I didn't want to take up too much time. What I end up getting is for the sum of squares factor, I get 215.92. And clearly the degrees of freedom for the factor is 2. And I get for the sum of squares for the error, I get 374.12 over the degrees of freedom, 21. When I divide this out, I get 107.96 over 17.81. So my F statistic, I didn't do that, so let's see, so we have 107.96 divided by 17.81, I get 6.06. All right, so again, to calculate the p-value, we are drawing from the F distribution with degrees of freedom 2, 21. We are interested in the area to the right of 6.06. So guys, we can do that. So we will have 1 minus PF, 6.06, comma 2, comma 21. So our p-value is 0.0084, which is clearly less than 0.05, so we achieve statistical significance. So what that tells us is of our null and alternative hypothesis, that the mean for Professor B equals the mean for Professor B equals the mean for Professor C versus since our p-value was less than alpha, what was it? I forget now. 0.0084. We reject that statement and conclude that, in a sense, this is the more reasonable statement. It appears there's at least one pair of means. We don't know whether there's one or two. We don't know what pair of means are actually different statistically, but we are led to believe that from the F statistic. Now, guys, let's see how this plays out on R. So I'll make this larger and we'll see how we typically conduct an ANOVA. So first thing I would want to do is I'm just going to call up my model, and I'll use the AOV function. And I want to do my score over my prof. I'll do summary model. And when we get our output, we'll see some very, very familiar values. Now let me go back split screen on you here. Taught this class one time. The very first time I taught the class, I took too much for granted, and I think it ended up coming back in the end and haunting me slightly. But so I've just I'd rather go into more detail, I guess. So the 215.92, you can see falls as I've highlighted on the left side, is the sum of squares for prof. Well, prof here stands for the factor term, degrees of freedom 2, degrees of freedom 21, and you can see the 374.12 is what R calls the sum of squares for residual. Now, guys, this whole ANOVA approach and regression approach all meets out there someplace what we call a general linear model. And but we'll get into that a little bit more. So the 107.96 is the mean square, the 17 mean square for the factor. The 17.81 is the mean square for the error or residual. And of course 6.06 gives a p-value of 0.0084, which is statistically significant at the 0.01 level.